Good morning, friends. I welcome you all on 30th session on system software. So before beginning, I just want to listen your, I don't know, means your sign that please raise your hand for 1 second so that I will understand you are able to see my video as well as slide on your desktop or mobile phone. Thank you, Chetakshi, Chinmay, Aishwarya, Mandar, Abhishek, Homeshwari, Tanuja, Disha, Anishraj, Abhishek, Om, Srikant, Sakshi, Rasika, Sahil, Gauri, Anurag, Sonal, Nayan, Gunjan, Aishwarya, Tejas, Suyog. अरे तेजस सुयोग ने हाथ नहीं वर केला. Hello Tejas, you are not raising your hand. Tejas, Suyog आणि Srikant, am I audible to you? Shivani.
Yes, sir. Audible, sir.
Thank you very much. So I begin today. You have to just relax. So I am not going to give you any big, heavy mental burden. Today we are near to finish. So I will just begin. So friends, we are near to end of this unit. We have almost covered the sheep reduce parser, means concept, then concept of the bottom-up parser, rightmost derivation in reverse order concept, then concept of constructing the parsing table using typical algorithm, SLR parser, CLR parser, and today we are going to see LR parser. Actually, it is very same thing is there. Minor modification is there. You don't have to, and you can use same example, grammar examples, whatever we have learned. I have taken typical examples so that normally they are generally asked in exam, like expression grammar. So so let us see the agenda. We are going to see, I will try to introduce what is the LR parser, look ahead LR parser, how to construct the LR parsing table. And definitely, I'm continuing the previous example for understanding in detailed way. And I will take one more example on CLR as well as LR. So don't worry about it. And I will be floating one PDF file that will be complete solution from start to end with all the necessary steps in detail, like step 1, step 2, what you have to do in designing particular parser and processing particular given string, along with justifications. So last time we have seen this example, simple grammar with 3 production rules, and we want to construct the canonical set of atoms, LR1 atoms, then LR1 automata, we call it as a DFA, and then parsing table. We have seen this thing. I will just go through as a recap. I will go through it, and then we shall understand what is a LR parser. So as usual, you know, the given grammar is there. We have to create a new augmented grammar by adding new start symbol. So this is how it is done. Then there is algorithm to construct the LR1 atoms, set of atoms. So go through this algorithm. I suggest you to read it line by line, try to interpret it. I have already given you simple steps. This is a summary of that algorithm. So what it states. So whatever LR1 atom contains 2 things. One is a LR0 atom, and second, separated by comma, is the leukoid symbol. It may be 1, 2, 3, 4. It depends. So A is representing some terminal. And please also note that whatever the first and follow set are there. So these are nothing but these are leukoids in that particular grammar. So if there is some production rule like this, where dot is in front of some capital letter like B, then in given grammar, there can be multiple production rules, like beta giving you gamma. So we have to add such rules into the closure set. And we have to compute the leukoid for newly added production rules by using uh, this pattern matching like logic. Means we have to understand what is alpha, what is capital B, what is beta, and what is A in given LR1 atom. And depending on that, we have to concatenate beta and A together. So sometimes beta can be empty or epsilon. And we have to take combine post of this. So first is a algorithm. And we have to add this B, small b, as a lookup item into newly inserted production rule. So I suggest you to download the PDF number 12 from the FTP site, or you can watch the video, or you can go through the MS Office 360 Office from the class material resources. You can download all the material. So last time we have seen, we have computed 0 to 9 items, LR1 items, set of atoms. So these atoms are representing its complete state of some DFA. And we also, last time I have shown there are around GOTO statements are there. So what we are doing, we are actually shifting this dot one place ahead. So in this way, we are getting some transitions on GOTO. GOTO is a algorithm. So for example, here I am choosing I2 set. I2 set contains 3 production rules, and it has only one lookup symbol, dollar is there. Now, here we are considering it is a transition on small c, second number production rule. So what is happening? When we consider GOTO, so what we do, we simply shift the dot one place ahead. So that dot will be in front of capital C, and it will be at the end of small c. So it is represented in a closer line, and it will contain the lookup symbol as it is from the original set, that is I2. Now we have to add this production rule. This is called as a basis item, or you can call it as a basis production rule. So whatever is there in closure, this bracket, closure is a function. So you can compute closure of multiple production rules. So for that, you have to refer previous examples. So there can be some situations where you will compute closure for multiple production rules, where dot is in front of, say, capital C. So there will be 3 or 4 production rules. So now here, luckily, there is only one production rule, so there is no problem. So rule is that keep this closure atom as it is into the closure set. Then dot is in front of capital C. So you have to refer the original grammar. For example, in a red color bracket, C is giving you small c and capital C, and C is giving you small d. Rule number 2 and 3 from original grammar. Now we have to add C production rules, rule number 2 and 3. But we have to compute the new lookups for these 2 production rules. So these are computed like this. It is given on the bottom area of this slide. On one slide, in shaded area, there is algorithm. And on one side, left side of that box, in blue color, I am representing alpha, B, and beta. Now, if you match this, so alpha is a small c, dot is something, B is a non-terminal where dot is in front of it. Dot is in front of B. So here in this case, capital C is a B. And beta, there is no string, so we can assume beta is as a empty, or you can assume it as a epsilon. And the terminal or look ahead is dollar. So ultimately, first of beta A, so beta is empty. So first of dollar will be as it is. And that's why dollar is added. So please note this thing. For example, if you study I0 set, you will find that first two production rule contains dollar as a look ahead, and second two production rules contains C/D, C or D, like this. So every time you have to compute, when you add the production rule, you have to compute the look ahead item as per the algorithm. So only that difference is there. So if you do practice by writing that example in your copy, one or two examples, you don't need to work out on many examples. If you write two examples in your copy, then your mind will accept that thing. How the new look aheads are computed. So in post production rule, it is taken as it is from the closure set. But remaining production rules, which are taken from the original grammar set. So for every production rule, you have to compute the new look ahead. So this is the difference only. Otherwise, rest mechanism is same, which is applicable for SLR parser. So this step is sufficient. And here we have seen that there are 13 GOTOs are there. So means 13 edges are there. Then again, we have to understand how many boxes are there where dot is at the end of the RHS. So here you will find that I1, I4, I3, I7, I8 and I9. These are the sets, canonical sets, LR1 sets, where dot is at the end. Sometimes it may happen that a set contains 3 or 4 production rules, but only one production rule has dot at the end. So we have to only think about it. So luckily here only single production rule is there in each box. But in many times it depends on the structure and design of the grammar that out of 3 or 4 production rules, only one production rule contains dot at the end. So what is that? When dot is at the end, it means that it is a reduce action. If dot is not at the end, it is a shift action. So that's why what we have done, we have written those sets in table along with the rule numbers. These rule numbers are referred from original grammar. Then we have LHS and RHS. Now in case of CLR parser, we don't need the follow. We don't need the follow at set. We need only look at which are in a set itself. But why I am writing this? Because you may not miss anything. You should not miss anything. So it is better to write all the follow items also along with the LR1 item. So second column is representing LR1 item along with the look ahead, and fourth column is representing follow items of respective non-terminal. And the action is there, R3, R1 or whatever. It depends. That is a dot is at the end, so we have to reduce it. So that is there. So this will help you in designing the DFA. So this is the diagram given in your book. You can use same diagram, no problem, or you can draw it on your own. So you know this, we have to map action as well as GOTO. So action contains only terminals. You know what are the terminals, and GOTO maps only non-terminals. And whatever the DFA is there on capital letters, on transition of capital letters, you can put those numbers in the GOTO columns, S and C. And shift, you can easily understand it. Normally shift is related with the terminal. So S3, S4 or S7, whatever. And in red color, R3, R1, R2 is there. So these are the reduce actions as per the table. So it is very easy to design a parsing table from the given DFA. So the main thing is that you should have all canonical set of atoms. You should compute them correctly. So if you miss something, so your table will be wrong. And whatever you do parsing on the given input string, that will be also wrong. So it is the best way to use such kind of table to map all the reduced sections. So from this here, see in this table, if you see the I5, there is a reduced section 1. So, and if you refer the parsing table in 5, state number 5, so there is R1 there in dollar column. Why dollar column? Because in I5, dollar is represented as a look ahead. Dollar is represented as a look ahead. So there can be multiple look aheads. You can take the example of say state 8. So in state 8, there are 2 look aheads, C and D, and rule is rule number 2. So on C and D in action part, you are writing R2 in C column and D column with respect to state number 8. And in case of state number 9, you are writing R2 with respect to dollar, because dollar is a look ahead symbol in that respective production rule where dot is at the end. So in this way, you have to keep these things in mind. Once you do 1 or 2 examples manually on your own, then you will be comfortable. You will be able to solve any problem, even unknown grammar also. Because this is mechanical. It is not a, it's a mechanical. You have to follow the logical steps 1, 2, 3, 4, 5. If you follow the steps correctly, your answer will be correct. Even if that grammar is new to you, you have not ever seen that grammar, you can compute the things. Only your practice will make you that you will be able to compute it in less time. So this is a CLR parsing table. Now see here, we have learned about the same grammar. We have computed and we have designed the SLR parser for same grammar. Try to recall that. How many states are there? And we have computed CLR parser for same grammar. So here you are getting 0 to 9 means total 10 states you are getting. Now let us see how to construct LLR parser for same grammar. So that is also easy. This is an example where we are trying to parse CDD as a given string. So I have last time talked about it. This is a complete solution, slide number 16. This was a slide number 15. But why I am keeping it blank? I want that you should do it on pen and paper on your side to get more confidence. And in the last column, that is a remark column, the steps are explained: how to compute GOTO, how to pop the atoms from the stack, and how to push the LHS, that is a handle of the production rule during the reduce action. That everything is explained there. So go through it coolly, take your time, read it 2 or 3 times, then you will understand. You will not need to read it again 4th time. So anyway, this was about the CLR parser. Now, I just want to recall that before the announcement of the dates on test number 2, in same week, you have to submit the TEC component. I already told you that case study is there, programming assignment is there, presentation, demo, and video clip is there. You have to use these tools to submit. And these are the topics. I hope that you have the screenshots. So take the screenshot if the students who have not taken screenshots of this slide number 18. You have to select those topics. You have to Google and you have to learn. Case study means what? You have to learn about new topic and you have to generate some report and you have to submit that report. So this is another slide. So 20 points are, means 20 topics are there, areas are there. You have to submit it. So most I will prefer programming and demonstrations and presentation. And those who will be going for the 18 point, that is a demonstration, I will be giving them extra marks. Those who will be doing programming on EAC and LEX, I will be giving some more weightage than regular. Anyway, Now, this is same grammar. We are trying to understand how to construct the LALR. LA means look ahead. LR means that you know. So when I say LR, it means that you have to assume that it is a CLR parser, canonical LR parser. When I say SLR parser, you have to assume that it is a SLR1 parser. Please note this thing. You might be confusing. But when I say SLR parser, it means it is a SLR1 parser. One means there is only one look ahead symbol like this. So that is convention. I don't have means, but you have to go through it. It is a theoretical conventions. We don't call SLR parser as a simply SLR parser. We cannot call some parser as a SLR0 parser. There is nothing there. There can be SLR1 parser or 2 parser, SLR2 parser or SLRK parser. So I again suggest you to go and get the definitions of the grammar. So you should be able to write the definition. So suppose I ask you, what is SLR grammar? What is SLR1 grammar? So you should be able to write a definition in 1 or 2 lines and 1 or 2 examples, small examples like this. For example, this is an example of a grammar. So people may ask you in exam or even get a questions also. Identify whether given grammar is LR0 or LR1 or something like. So you should have definitions, standard definitions, and those definitions you will get from that book I have already provided to you. So let us see how to construct the LLR parsing table and how to compute the processing of particular string using the LLR parsing table. So method for constructing LLR parsing table as well as method for computing moves on particular input string is same with respect to CLR parser. Minor changes there. I'm just going to tell it. What is that? So here 4 steps are there. These are the broad steps. You can take this screenshot like something. Now you know what is the LR1 component, what is LR0 component. So first you have to compute the LR1 component for generating the LLR parser. Second step is that we have to compute the LR1 DFA. Or if you skip this, but you should not skip it because if you design DFA, it will help you to design correct parsing table. So don't skip this second step. So you have to compute the LR1 DFA. Then you have to identify common sets. Common sets. I will be showing you what I mean. You have to find the common states. So sets means I0, I1, I2, I3, and states means 0, 1, 2, 3, 4, whatever your DFA states are there. And if you identify common states, then you have to merge them. So you can recall your TOC in that equivalent states are there, and we merge them, and we can reduce the size of the overall DFA or NFA. And once we merge the states, then it means what? We are reducing the number of states in a CLR parser. So once you merge them, you reduce the number of states, then you can start constructing the parsing table. So parsing table construction algorithm is also given in the book. I have already given you algorithm in slides. In beginning, I told you that all those algorithms for computing first, closer, GOTO, and parsing table construction and parsing algorithms. Say parsing table construction is different algorithm, and parsing algorithm is a different algorithm. So same algorithm works on all types of the parsers like SLR, CLR, and LLR. So refer previous 2-3 PPTs, you will get the algorithms. Now, let us see. These are the, let us say we have computed LR1 atoms, set of LR1 atoms, canonical set of LR1 atoms, and we have computed correctly all the states from I0 to I9 as per the previous mechanism. Now, here, I'm just giving you, see, you have to observe it. So problem is that if your number of sets are more, for example, here 0 to 9 is there, but there can be some grammar where there can be 24, 25 sets can be there, states can be there. So it is very hard to do manually. Please note this thing. To manually compare the states. Now here, luckily, what is happening? Almost 3 or 4 maximum production rules are there in one box or in one set. But there can be some grammar where one set may contain 7 or 8 or 9 production rules. So in that situation, it is very hard to map equivalence between the sets. It is very hard. Let us see. See here, I am already giving you, for example, set number I3 and I6. I am coloring it. It is a bluish light. So I3 set is there and I6 set is there. So what is happening? Here LR0 atom is there. You know what is LR0 atom? LR0 atom is, that is a production rule with something dot somewhere, which we are moving. So LR0 atoms are same in I6 and I3. I hope you are able to see these. See, in I3, there are 3 production rules. In I6, there are also 3 production rules. Now, what is difference? In I3, look ahead is C or D, C/D. This is the look ahead. Or means it is actually OR. It is a, assume that it is a comma, not a divide sign. It is a OR, logical OR. So I3 contains 2 look aheads, C or D. But I6 contains only 1 look ahead, that is $. But almost all the production rules, RHS, all the production rules are same. So let us call them as a LR0 atoms, or you can call them as a core of the LR1 atom. I have given the definition of core also in a last lecture. So your core should be matching, and no matter whether the look ahead match or not, that is not a problem. But if there is a situation like this, I3 and I6, then you can group them into one state. You can make I36 as a one state. Now there is one more pair, I4 and I7. It is in a purple shade. I don't know whether you are able to see it or not, but it is in purple color. So see, both sets I4 and I7 contains only one production rule. I4 contains 2 look aheads, I4 contains 2 look aheads, C and D, and I7 contain only 1 look ahead, that is $. But their core atom is same. Their core atom is same. For example, C is giving you D dot. So in this way, there is equivalence. So friends, you have to merge them. That's why we have identified. Now, again observe set number 8 and 9. These are the last sets. So 8 contains 2 look ahead and 9 contains only 1 look ahead, and both contains same core atom. Now luckily, as I told you, that here very less number of production rules are there. But if a set contains 7, 8, 9 production rules and multiple look aheads. Luckily here only two non-terminals are there, C and D, small c and small d, and dollar is extra item. So if there are multiple look aheads and number of productions are more, then it is very hard manually to merge them or identify the similarity between the core components. It is very hard. So anyway, so from these three pairs, we can generate I36, I47, and I89 as a single state. So in this way, ultimately what we are doing, we are reducing the DFA, LR1 DFA. So let us see this. So this is a diagram. So I'm just unnecessarily showing you why, because you can draw in this way also as per your comfort, but please make sure that your diagram should show, your arrow should show correct directions. Then you should highlight capital letters and lowercase letters, because capital letters are representing non-terminals, lowercase letters are representing terminals. So you should highlight them. Then you should write clearly the state. For example, here I am writing I7 or I4. So in exam, you have to do like that. Anyway, so from this slide, what we are trying to understand, see here, three pairs are there, I36, I47, I89. So this is a previous parsing table, right? Previous parsing table contains 0 to 9 means total 10 states, and new parsing table contains 0 to 89 means 1, 2, 3, 4, 5, 6, and 7. Total 7 states. So CLR parser contains 10 states. That is the disadvantage of CLR parsers. Normally CLR parser is more very powerful parsing mechanism. Actually it is a mechanism, and it handles all types of programming language constructs like if then else, for, loop, and whatever, jump, GOTOs, and all that, parameter passing mechanisms, all that. But it is very hard to construct. That's why in practically we choose LLR parsers. LLR parsers are very efficient. It contains less number of states. It is very easy to design, and we can use some tool. So tool means what? YAC is there, YACC, and there is one more tool that is called as a Bison. You can write this Bison word. Bison, आपको पता है गवा करके रहता है जंगल में. So it is a name from that Bison. So you Google it. So Bison is nothing but it is a variation of the YAC tool. So what is there? You can provide the grammar only directly as an input to the YAC program or a Bison program, and you will get directly such parsing table. You don't need to compute the DFN and all that. You don't need to compute the follow set, first set, and all that. You don't need to compare the states and merge them and all that. It will do automatically. So that's why I suggested you to go and visit the FTP site. I have already given you the URL, and there are some PDFs on that site in particular folder, and you can download those PDFs, and it is a pictorial, means it is a explanatory. Any person, any layman who is downloading that PDF, it is pictorial enough. If you follow the steps, you will be able to learn how to write a program in YAC and how to write a program in Lex. So what I suggest is that you go there and visit here and try to learn, because maybe after unit test number 2 or class test number 2, you have to submit the practicals. So you have to submit your screenshots on your end. You have to run those programs at your end, and then you have to submit them. So it is the best way to be familiar with the resources. So visit the FTP site. If you face some problem downloading or visiting some site, then you just send me message on WhatsApp. I will try to resolve that. So friends, here what is happening? We have merged 3 and 6, right? So So what we are doing, whenever there is a reference of S3 and S6, we are writing S36 because we have merged them. Now 4 and 7 are there. You refer the previous parsing table, CLR parsing table. See in line number 0 and line number 3, 0 and third state, there is a, in a D column, we are using S4, right? So in a LLR parser, we are using S47 in D column. So that thing you have to understand it. Then if you refer the 36, state number 36 in a LLR parser, here there are two shifts, S36 and S47. Now you can tally it by referring the CLR table. CLR table में क्या है, 3 का S3 और S4 है, और C का जो GOTO है, it is 8, right? और 6 जो है, 6 state का क्या है, in 6 state there is in red color S6 and S7, and GOTO is there in same row, it is a 9. GOTO of C, capital C on is 9. So in 3.6 in LLR table, it is a 89, right? So in this way, what we are doing, we are merging them and we are preserving the equivalence. Means in other words, what is happening? This LLR table is equivalent to CLR table on grammatical level. Like, so here I have not drawn the diagram for LLR parser. Normally they very rarely ask you, but from this set, when you merge them, you can draw the LLR DFA. And what you have to do, you have to simply modify your GOTOs. Means you will get new GOTOs. Here I3 is there, I6 is there. You have to merge them, and you will get new transitions. So in this way, you can construct the diagram for DFA for LLR parser also, but it is a rarely asked. Normally they don't ask in exam. They simply ask for CLR and DFA for CLR, means LR1 DFA. So I have not drawn it. So it is pretty easy. You have to just merge them, and you can reduce the parsing table in new form, and that is called as a LALR. Now just think, I will be definitely telling you in next session. Today I am going to end this unit number 3. In next session we shall start unit number 4. But I will be putting 2 or 3 slides on error handling in a bottom-up parser and something about the LLR parser. I will take one more example. Today also I am going to show you one more example. So this is the way. Anyway, this is one grammar. Again, it is asked that you have to compute the CLR parsing table for a given grammar. Now here in this grammar, there are 5 production rules are there. And note here, there is a one unit production rule, that is R is giving you L at the last. Now again, you have to compute first and follow set LR1 items, set of LR1 items, then LR1 DFA, and then you have to construct the CLR parsing table. Now, always first task should be that you should identify what are the terminal symbols. Here, star and equal to, these are only 2 terminal symbols, but there are 3 non-terminals. You should note this. Now, you have to just number them. You have to augment the grammar like this. You have to give some numbers like 1, 2, 3, 4, 5, like this. And you have to keep these numbers very fixed, because you know you have to refer these numbers in parsing also. Now, it is a straight grammar, so you can easily compute first and follow set. For example, follow of L. Now you see the first rule, L equal to R. So you can easily get it is a follow of L, following L. Anyway, now we should be able to draw the DFA for this grammar. So for that we have to compute the sets. So let us say these are the sets. So here from I0 to, let us say, I8, I9, there are LR1 items. Now you can take the screenshot and then you can write. See here there is a little difference. For example, there are some states like I5 and I5 dash. See, I don't know whether you are able to see my arrow of mouse pointer on your end or not, but this is I5 and this is I5 dash. Then again, there is a I7 dash and I7 is also there. It is in the bottom. Then there is a I8 dash and there is a I8 also. It is again it is in the bottom in second row, sorry, column. So in this way, here dollar equal to these are the only two terminals or lookaheads, and it is computed. Arrows are given there, transitions are given there. So this is directly, and if you do the practice, you can directly construct the DFA. You don't have to. What you have to do is that you have to just club the similar items. For example, where means you have to collect all the production rules where dot is in front of capital S, and then you have to shift that dot one place ahead. For example, I0 to I1. Then you have to collect all L production rules where dot is in front of L. For example, last production rule in I0 and second production rule in I0. Here dot is in front of capital L. So when you do GOTO, means you are shifting that dot one place ahead. So see I2 set on capital L, blue color is there, and I2 is given in red color. And see what you have done here. You have combinedly shifted dot one place ahead by considering only L items. L means L is a non-terminal. So if you do the practice, there is no need to do that closure and all that. But for theory in exam, for getting marks, you should go and follow the steps, whatever I have distributed in terms of PDF on your WhatsApp. But if you work out on 2 or 3 examples, you will be able to directly draw the DFA. There is no problem. For example, there is only one R production rule where a dot is in front of R. If you think about the I0, so there is only one transition from I0 to I4. See, I4 is at the bottom in first column. So dot is shifted. Now here what is difficult? You have to compute the lookaheads every time. You have to consider capital B, beta and small a every time. You have to refer. So best way is that initially you do with detailed steps in your copy. Now here, for example, second production rule is there in I0. So dot is in front of capital L, right? Now L is generating 2 production rules. See, rule number 3 and 4 in a given grammar. Rule number 3 and 4 in the given grammar. Now you are putting dot in front of all the RHS, and then you are writing equal to /$. So you have to think how this dollar and equal to came. See, in I0 box, fourth and fifth production rule. Here lookaheads are equal to /$, and rest of the lookaheads are simply $. So anyway, I will talk about it in detail. I will be putting one PDF on your WhatsApp, and it will we shall compute every state in detail by shifting the dot, by doing the GOTOs, and by doing the computing the closure of that, and then collecting all the GOTOs and then drawing some DFA like this. I will be putting, it will take, means if you do it in detail, it will take 3 or 4 pages simply. So you can refer previous PDFs, whatever I have circulated on your WhatsApp. You can use same logic here. So here only difficulties with careful computation of the new lookaheads when we add something. Now, anyway, I will not talk more. Now, what I want to say is that here, when I say I5 and I5 dash, so what I want to say is that I5 and I5 dash, they contain same core item and different lookaheads. For example, I5 contains 2 lookahead, and I5 dash, which is just next to it, it contains only 1 lookahead. It contains only I5 dash contain only $ as a lookahead, and I5 contains 2 lookaheads equal to and $. In same way, I dash is there, I8 dash is there, I8 dash. So it contains $, and there is a second column, last box is there. It contains 2 lookaheads equal to and $, in green color. So these are the equivalent states. So what I want to say is that whatever dots are there, dash is there. Sorry, whatever the dash is there, I5, I8, I7, I3, means I3 and I3 dash, like. So these are the equivalent states. That's what I want to say. They contain core atoms, similar core atoms, same number of production rules. See, you have to take care. If one box contains 3 production rules and third box contains 4 production rules, even though there is a matching, you cannot merge them. It must contain same number of production rules. If there are 3, then both boxes must contain 3 production rules. So that is there. Actually, it is a logical. I mean, there is no need to tell these things. You have to interpret it. You have to understand it. कि भाई production rule तो same होने चाहिए. If lookaheads are not matching, anyway. So in this way, there are 3-4 things are there. So in this way, we can reduce all these states. So just count the number of states: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So this CLR Parser contains 14 states. You count it. And let us see this as a homework. I'm just closing it. Please note, I'm not taking more time. So you have to construct the parsing table from this DFA as a homework and try to submit, try to send the photo of your copy to me on WhatsApp, personal WhatsApp. Now here, I want to say that I3, I dash, I5, I5 dash, I7, I7 dash, I8 and I8 dash is total 1, 2, 3, and 4. 4 pairs are there. So we can reduce 4 states. So SLR parcel will contain 10 states. CLR parser will contain, see, I just told you, when I say LR1 parser means that it is a CLR parser. Don't confuse it. So CLR parser contains 14 states and LLR parser contains 10 states. Why? Because out of 14, we are minusing 4 states. 14 minus 4 is equal to 10. So that is how it is there. So you read this slide, later download it. And then in this way, we can merge them and we can construct a machine or DFA for LLR parser. So this is the LLR DFA. So it contains only 10 states. You can count it. Here we have merged 5 and 8 and 3 and 7. So in this way, there are only 10 states. Now, from this, you can construct the parsing table also. So it is the best way to construct the CLR parsing table first, and then construct the merge states, and then LLR parsing table, because that will be very easy. I have shown you side by side CLR parser and LLR parser for previous example. So that will help you. So anyway, I am near to close. So construct the LLR parsing table for this example and send your screenshot or photo to me on my WhatsApp, so that I will trace that what is happening on your end, whether you are able to understand me or not. Anyway, time is over. I am going to complete it. Next time we shall start fourth unit, but I will cover one more example on CLR as well as LRR in detail for people those who feel awkward in understanding it. Anyway, thank you very much for listening me patiently. And as I told you, try to select your TEC component and prepare material for it, because assignments are not simple. You have to work out, you have to Google, you have to read material. So friends, I am going to end. Thank you very much. Thanks for listening me. Take care. Take care of your family and yourself, because 7 or 8 months are too much. It is very distressing, and keep your moral high and keep learning. I suggest you to join some online courses like on Coursera or whatever, maybe Edureka. Join some courses. Like, don't go for Python only. Python not. You go for machine learning or deep learning or data analytics or big data or DevOps. I will be talking about in a maybe 10 or 20 minutes what you should learn at your end. You can utilize your time, because only 2 hours lectures are there. So instead of wasting other time, you can upgrade your skill. Anyway, thank you. I'm closing.